Welcome to this Key Stage 4 lesson on nuclear fusion. So let's start by looking at what nuclear fusion is. Well, the definition we need to know is that nuclear fusion is a process in which two small atomic nuclei join together to become a larger nucleus. So, to understand nuclear fusion, let's look at some small nuclei. We have here three different isotopes of hydrogen. We have the normal hydrogen, which is the most common in the universe, which has one proton. Then we have an isotope of hydrogen called deuterium, which has a proton and a neutron in the nucleus. And here we can see that its atomic mass is 2, but its atomic number is 1 still, because it's still hydrogen. And then we have another isotope of hydrogen called tritium, where it has 1 proton and 2 neutrons. So here we have an atomic mass of 3 and an atomic number of 1. Now these are all chemically identical, because they all have 1 proton, which means when they are neutral, they all have 1 electron. So they are all hydrogen the element, but they are 3 different versions of that element called isotopes. Now, fusion is not easy. For fusion to occur, the two nuclei must have enough kinetic energy to overcome the electrostatic force of repulsion between the positively charged nuclei. So let's consider the center of 2 hydrogen atoms. Each one has a proton inside it, and we'll know that protons are positively charged from a previous lesson. So if I'm trying to get 2 positively charged things near each other, we know that they repel. We know that like charges repel and opposite charges attract. So it's very difficult to get 2 protons to fuse together. In order to do so, they need to be traveling extremely fast so that they can overcome that electrostatic force of repulsion. So to provide enough kinetic energy to the nuclei, the substance must be heated to a temperature of several million degrees. By heating it up, you make the particles move faster, until they are moving so fast that the protons are able to overcome the electrostatic force of repulsion. Now, this is a key phrase that you need to know for your examinations. A common question that comes up in all exam boards is, explain why high temperatures are needed for nuclear fusion to occur. The answer is to say, to overcome the electrostatic force of repulsion, that's 1 mark, between the 2 positively charged nuclei, and that's your 2nd mark. In a nuclear fusion reaction, the products actually have less mass than the reactants, as some of the mass is converted into energy in the process, due to something called the mass-energy equivalence. This you may recognize as E equals mc squared. It turns out when fusion occurs, energy is released because some of that mass decreases. The energy and mass are equivalent, and so the mass is in fact converted into a huge amount of energy. And that energy either gets stored in the kinetic store of the particles after the fusion, so after fusion the particles will be moving quite fast, but also it will be transferred away by gamma rays. Those gamma rays have a high frequency and therefore have a large amount of energy being transferred. So, nuclear fusion equations. Here we have 2 isotopes of hydrogen. They collide, and you can see by the star and the 2 waves, I've represented there that there is an energy released in this reaction, and those two waves represent gamma rays. There are two gamma rays being released, traveling in opposite directions. And then finally, we have a new atom, or a new nucleus. So the first thing I want you to do is identify the names of all the nuclei you can see on screen. Pause the video now to do that before I give you the answer. So on the left, we have two deuterium atoms. So they are both hydrogen, but they are deuterium because they also have a neutron inside each atom. When they fuse together, they produce helium. And so the next thing we need to be able to do is to write the nuclear equation for this reaction. So pause the video now if you want to give this a go. First of all, we have deuterium. It is written with a mass of 2 and an atomic number of 1. We have a second deuterium, and then they react. We use the same symbol as we would in a chemical reaction, only this is a nuclear reaction because we are observing changes to the nucleus. This produces a helium nucleus along with 2 gamma rays. So here we're having the release of a huge amount of energy. And in fact, nuclear fusion reactions can be self-sustaining if they produce enough energy in order to make the particles in the area move faster. So it will heat it up. When nuclear fusion occurs, the temperature will increase. That will give particles more speed, which means more particles can overcome the force of electrostatic repulsion, and so more fusion will occur. So it is possible to make a self-sustaining fusion reaction. However, we have not yet done that on Earth. So having seen this version, I would like you to copy down the diagram as well as the nuclear equation before we move on to the next slide, where I will ask you to attempt the same again. Draw the nuclear reaction and then write out the equation. So here we have a different pair of isotopes fusing together. So this time I want you to draw it out and then draw, or write out, I should say, the nuclear equation. Pause the video now to give that a go. So here we have it. First of all, we have tritium at the top left. So tritium is hydrogen with 2 neutrons and 1 proton, making its atomic mass 3 and its atomic number 1. Then we have hydrogen on its own with an atomic mass of 1 and an atomic number of 1. And they join together to make helium. And when this happens, there is a huge release of energy and we get 2 gamma rays. Correct yourself if you got the equation wrong. And let's move on. Our final nuclear reaction, our final nuclear fusion reaction. Here we have again 2 different isotopes, but we've got something extra now. So, pause the video to attempt this yourself. And here we have the answer. First of all, we've got tritium at the top left. That is being combined with deuterium, and this produces not only the helium nucleus, but there is a spare neutron. And finally, we also get a huge release of energy. We get 2 gamma rays transmitting energy away from the system. Note as well that the helium nucleus and the neutron will be moving extremely fast, so some of that energy will be transferred to the kinetic store of those particles. So you need to be able to describe the conditions for nuclear fusion, explain why they're necessary, and write out a nuclear equation. And that's the end of the lesson.